All right, good morning, everybody. Good morning from Cambridge, Massachusetts. Good afternoon and good evening to those of you who are joining us from the other parts of the world. My name is C.J. Guo. I'm a program director with the Office of Corporate Relations Office at MIT. In this office, we have a very strong Industrial Liaison Program and a startup exchange platform through which we connect many of the world's most innovation-centric companies to MIT's leading science and research and technology development activities. Myself, I'm also an energy veteran. I worked in the energy industry for many years before I joined MIT about 4 years ago. So you know, the energy sector is facing unprecedented challenges today with a global COVID-19 pandemic and historically low energy prices, complicating an already difficult transition towards a low carbon future. But we'll meet the challenges. Hopefully we'll come out of the other side in better shape. So we have to take actions. Some of the action we're taking, including engaging in forward-looking collaborations in technology development, innovation, and problem solving, which MIT does the best. So this month, the Industrial Liaison Program and MIT Energy Initiative are jointly presenting a energy innovation webinar series. Today's session, called Energy Transition and Economics, is the first of the 3 planned sessions. The next session will happen next week, May 13th, same time. And the third session will be on May 21st, 10 a.m. We've assembled a group of leading experts and researchers from MIT to share their insights with us. So together we'll be better able to navigate these difficult times for a sustainable energy future after the current crisis. So with that, I'd like to introduce our first speaker today and also the session monitor, Professor Bob Armstrong. You know, Bob is the founding director and current director of MIT's Energy Initiative. I won't have time to go through his long list of accomplishments today, except to say that Bob was elected to the American Academy of Engineering about a dozen years ago. And he was elected to the Academy of Arts and Sciences a couple of weeks ago. So our congratulations to Professor Armstrong. So with that, Bob, please take over. Thank you.
Thank you very much, CJ. Pleasure to have a chance to do this webinar and the 2 following webinars. As you mentioned, CJ, this is a critical time for the world. We're facing a huge challenge, not just with the coronavirus, although that's the challenge immediately in our face day in and day out. But we have an enormous challenge meeting climate change. I think, among other things, over the next 3 sessions, we'll reflect on what that challenge looks like. And today, we'll do a lot of work trying to frame that challenge, talking about the system itself, the energy system, and how that is interconnected across the economy. And in the next session, we'll talk about some specific technologies that are important in getting to a zero or net zero carbon world. And then in the final session, we'll look at a specific sector in energy, the power sector, and look at some really interesting challenges there. So let me start. So let me start with framing the grand energy challenge that we have. That's a dual challenge, a dilemma of sorts. On the one hand, we project a substantial growth in energy demand globally, doubling or so by end of century. And at the same time, it's clear to all of us that the world urgently needs to reduce emissions in order to deal with the most serious effects of climate change. At the Paris Agreement back in 2015, we set an international goal of a 2 degree or a even better 1.5 degree temperature rise. And if anything, it's become more apparent to us that we need to be closer to that 1.5 than to 2 degrees on the one hand, and on the other, it's a really challenging goal to get to. Here's a graphic example of what that challenge looks like. This is a set of measurements taken on Mauna Loa. It's an observatory which we measure. NOAA measures CO2 concentrations. And you can trace over the time these measurements have been made by NOAA the rise in CO2 from about a little less than 320 parts per million up beyond 400 parts per million. We crossed 400 parts per million for the entire year for the first time in 2016. And as of last month, we're a little over 416 parts per million. So we continue to grow fast. If we look at the nominal concentration of CO2 that we associate typically with a 2 degree temperature rise, sort of this first goal of the 2015 Paris Accord, that's about 450 parts per million. And if you do a simple extrapolation of the multi-decade curve on the left, you find that you would cross 450 ppm somewhere around 2037. So we don't have very far to go before we hit and surpass a 2 degree limit. The more challenging problem is the preferably 1.5 degrees centigrade rise articulated at Paris. If we continue on the trajectory in this curve, we'll hit about 425 ppm, or roughly the 1.5 degree, in maybe 7 years. So it is an immediate problem, no longer a very long-term problem that we face. A way to frame the challenge in terms of energy use is shown here. These are results from the Joint Program on the Science and Policy of Global Change here at MIT. This slide was in particular supplied by Sergei Paltsev, who's their deputy director. And this looks at one of the scenarios, one of the many scenarios that they've done, looking at global energy demand growth and how that's met by different energy sources. This particular scenario looks at what they would call a COP21 scenario, or a Paris forever scenario, in which we assume that we meet the COP21 targets, but we don't do anything else beyond that. That is, the policies that were put in place to get to the COP21 targets are left alone, but we don't do anything else. And what jumps out at you from this graph is that won't get us where we need to go. You see that the energy demand globally doubles roughly by end of century. You see we continue to use large fractions or get large fractions of our energy from coal, oil, and natural gas, so from fossil energy resources. 75% of our energy by mid-century is still from those sources. And so probably not surprisingly, the temperature rises we expect in a Paris forever scenario are too high. So by 2050, the central estimates from this particular scenario is about 2.2 degrees centigrade, so we've busted the 2-degree target already. And by 2100, the central estimate for temperature rise is about 3.7 degrees centigrade, way too high for a sustainable future. So what do we do about that? And that's what I want to frame in this opening presentation. And to do that, I'll look at the greenhouse gas emissions in a no policy scenario. That's assuming that we don't do anything differently. Going out to 2100, broken down by sectors. So the idea in this graph is to look at emissions from land use, from the 4 major energy sectors: electricity, transportation, buildings, and industry, and then non-CO2 greenhouse gas emissions. And in this graph, you can see a set of bars. These bars represent the band of projected emissions in 2030, 2050, and 2100. And the bars come from the set of scenarios run by, I think, about 1,400 different modelers participating in the annual assessment 5 working group 3 work in the IPCC. What you'll see is that the electricity sector is the tall pole in the tent here, and that's why we focus initially in going after the electricity sector in emissions. You'll also notice that there's quite a bit of uncertainty in total emissions going forward. So that's something to keep in mind here, that none of these models are absolutely certain. We could go about this at requiring net zero or zero emissions in each of these sectors. We could look at policies that allow us to go negative emissions in some of these sectors. And I'd like to consider that and just show you what the benefit of that could be in a scenario here, looking at a 2-degree scenario, say a 450 ppm CO2 equivalent, in which we allow carbon dioxide capture and storage. So the idea in CCS or CCUS is that in a sector like electricity, if I capture CO2 from flue gas emissions and then sequester that CO2, it is possible, if there's sufficient economic incentive, to go negative in the electricity sector. The virtue of that is it allows you to leave some of the more expensive to decarbonize aspects of other sectors alone, or to minimize what you have to do there, while still reaching net zero economy-wide. So you can see in this scenarios that land use emissions go to roughly zero, but emissions in some of the other difficult sectors, industry, for example, or transportation in particular, where air transportation it will be particularly challenging to decarbonize, that stays positive in this scenario. To put a little more flesh on the bones for that picture, let's look at a scenario in which there is significant negative emissions technology. This is, again, work from the joint program. In this case, the idea is to do negative emissions technologies by generating electricity from burning biomass grown specifically for that purpose, capturing the CO2 and then sequestering it. So there are two scenarios here. The upper curve represents a no BECCS scenario, or this no bioenergy plus CCS. The lower curve represents a world in which we allow the negative emissions technology. So we allow use of bioenergy and negative emissions technologies. And you see a number of striking differences between the two. First is that if you allow BECCS, then we use a lot more electricity. in the system. If we don't use BECCS technology, then to meet a 2-degree target, the number of terawatt hours globally is somewhere north of 45,000, where it's north of 70,000 in the BECCS scenario. You'll also see substantial use of fossil energy technologies at the bottom of this graph with CCS, still coal around with CCS, gas with CCS. It doesn't have to be. You could have other policies to govern those. Interestingly, the cost of carbon in order to get to 2 degrees in the top scenario is about 3 times the cost of carbon in the bottom scenario, in which you allow the negative emissions, so that it's economically much more affordable to get to this 2-degree target if we allow negative emissions technologies. So negative emissions allows us to get economy-wide decarbonization more efficiently. To get there, we need some specific technologies, specifically better technologies for capture. Now, this is an example of such a technology. This is an example of a suite of technologies actually out of Professor Alan Hatton's group in chemical engineering. Professor Hatton has been exploiting some interesting opportunities in bringing electrochemical approaches to carbon capture because of its ability to significantly lower costs for capture, including parasitic loads on power plants if you implement it. I'm not going to say very much about this now because Professor Hatton will be in next week's seminar talking about some of the new electrochemical techniques he has. This is actually an electrochemical process very similar to what's done today in amine capture, but one that allows, instead of a desorber running at a high temperature, which requires extra energy in the process, something that can be done at the same temperature as the absorber for the CO2. So much more efficient process. I think he'll tell you next week about some new electro-swing technologies where the entire absorption process looks a lot more like a battery, absorption between 2 electrodes, and one that could be used in a flue gas, in a power plant operation like this, or in direct air capture, which can be, I think, very interesting, very important if we go to negative emissions going forward. As we move towards deep decarbonization, which is, I think, the focus in this set of webinars, we need to go beyond single sector decarbonization. For example, in the power sector, the early work in decarbonization focused on generation technologies like solar, which were very economically attractive when they were at small penetration because they could replace peaking power applications. And so there was a lot of value in that. As we've gotten to higher penetrations of PV, we need to understand better how that excess PV, beyond what's needed for peaking, can be used in other sectors. And so this graph, or this Venn diagram, shows what we view at MITei as one of the big challenges today, which is understanding this sectoral coupling and developing the tools to allow us to do that analytically. This has been the basis of a development at MITei called Sesame. That's a sustainable energy modeling analysis environment. That is a tool that's been led by a research scientist at MITei, Emery Genscher, which looks at the sectoral coupling by looking at pathways for getting from energy sources to final use of energy, so that I could look, for example, at power, zero carbon power like solar energy or wind energy, and its application towards charging EVs as well as supplying power. Or I could look at industrial production of hydrogen that could be used for zero carbon processing, thermal processing in industry, or also used for supplying hydrogen for someday for hydrogen fuel cell vehicles. The idea in Sesame is outlined here, which is to, as I said, look at pathways that take us from energy sources all the way to end-use applications. The tool is very modular in structure so that it's easy to string together different pathways, and I've shown quite a few different ways to string together pathways from energy sources like oil or biomass or coal or natural gas, or if you look further in the middle of this curve, you can see wind and solar being used for fueling transportation applications. With this modular framework, stringing together different pathways like this allows us to look at more than 1,000 different pathways in the energy sector, covering some 90+% of all emissions from this sector. So it's a very robust and complete system in which the modular structure also allows you to do refinements of any of the modules. For example, if I want to substitute a specific wind turbine for some of the wind turbine, we have currently about 17 wind turbine models in the system. If there's a new one you want to put in, that's easy to do with the modular structure. The point I want to make with this graph is that there are a lot of ways to get from energy sources to an end-use applications. Each one of those has its own emissions profiles. You'll see in these different stages a little gray vector, a arrow that points up. That's the emissions associated with each one of these pieces, and you'll see the implications of that in the final life cycle analysis of different modes of transportation. But in the last presentation of today, Joanna Moody will talk some about specific examples in light-duty transportation, and I think give some more specific examples of analysis here. Before Joanna speaks, Elsa Olivetti, who's contributed in lots of different ways to the energy challenge. One specifically in one of our low-carbon centers is looking at supply chains for materials. She has looked at supply chains for batteries in our future of storage study. That's a major challenge we face going forward, and she's going to speak before Joanna. And then after me, Chris Knittel will talk about some of the economics issues, and in particular in the electricity sector, which plays big here. In the electricity sector, one of the big challenges we face is how to get to a carbon-free system, and what will be the needs of storage in such a system as we use ever-increasing amounts of intermittent or variable renewable energy resources. In the future of storage study that we have currently underway, one of the ways we're looking at that specific challenge of how much storage do we need and what kind is it, looks at an area like ERCOT, the Texas grid basically, and examines the solar and wind resources in ERCOT every day for a year. We've done this in multiple regions of the country and for more than a single year. But this illustrates what is done here. And you can see in the rows, days of the year, and in the columns, different months. The blue little sections are wind resource and the solar, the red parabolic regions are solar resources. The black curve on top is the total load. You can see in some cases you meet the total load with wind or solar or both, and in some cases you don't. So with data like this, we've been examining, and we is largely Patrick Brown at MITei, looking at how far can you get towards meeting the electricity system need with these variable resources if you build overcapacity for these, so that there's still adequate resource there, adequate generation there when the solar resource or wind resource is low. How much can you get towards a 100% renewable system if I add more transmission, interregional transmission or interstate transmission, and then what kinds of storage would I need in any of those scenarios, and what kind? And this is a particularly challenging analysis, but it is proving to be very interesting. Lastly, I wanted to mention that in addition to electricity as a generation technology that cuts across sectors, there are other technologies, chemical storage, hydrogen being perhaps the simplest of those, which also cut across sectors. And this chart is designed to illustrate that. On the left is low carbon electricity, so it could be variable renewable energy, wind and solar, which we were just talking about, which can feed into the transportation sector, so electrified vehicles, for example, feeds in a very simple way into the electricity sector, can be used in the industrial sector, for example, in converting thermochemical processes in the chemical industry to electrochemical processes, and can be used to provide heat, for example, and obviously lighting for residential and commercial uses. We can also do those things with low carbon hydrogen. I'll say low carbon because today we can get hydrogen most cheaply from steam methane reforming. You can make that a very low carbon source of hydrogen if you combine carbon capture and sequestration with the steam methane reforming. But in the long run, that's going to have too much carbon content, and we can get there through electrolysis. Although that's too expensive now, the goal is to drive those costs down as we continue to take advantage of SMR plus CCS as an opportunity to build up the infrastructure and the technologies for end use of hydrogen. So if you look at the gold bar going from right to left in this graph, you can see hydrogen also can play into these four different energy subsectors, providing residential and commercial heat, for example. In the industrial sector, it plays a role that electrochemistry can't in providing high temperature heat for thermal processes that we can't figure out how to convert into an electrochemical process. In the electric power sector, it is much more expensive than, say, solar or wind today. I think the opportunity space for hydrogen, there certainly in the short run, is for long-term storage. And then lastly, in the transportation sector, hydrogen can be used in the form of fuel for hydrogen fuel cell vehicles. Right now, those are more expensive, substantially more expensive than battery electric vehicles for light-duty transportation, and so it's not likely to play much of a role there in the immediate future. But there is a great opportunity, we think, in the transportation sector for heavy-duty freight, for heavy-duty trucking, for example, and perhaps in shipping applications, where range, rapid fueling, and so on is an issue. Already you see hydrogen as a preferred fuel for a zero carbon transportation in materials handling businesses, for forklifts, in warehouses, for example, where downtime is a major issue. So those two, I think, both play major roles, and this tool, Sesame, allows us to probe those and other specific technologies like generation technologies, fusion, for example, novel separations technologies, CCS technologies that you'll hear about next week, and then look at large-scale storage for the grid in week 3. So with that, I wanted to make just a few comments about why we should be optimistic. I think there are reasons why we should be worried. Obviously, we have not yet accelerated progress at a rate anywhere close to what we need to do. If there's a silver lining to the COVID-19 crisis, to this pandemic, one might be that it has certainly raised public awareness of some of the messages that science has been trying to give us over the last couple of decades, and which we've been pretty good at ignoring. One of those, of course, is the risk of pandemics. Another has been climate change. And so hopefully we take those messages, and as we come out of this current crisis, which, of course, not just affecting our health, but it affects our economy in a major way. And Chris, I think, will talk a great deal more about that in his presentation. So increased awareness, I think, is really important, and that was already evident in the public debate before the pandemic hit, but I think is certainly will be accentuated by that, and I think made a little bit more permanent in our minds. A second reason, I think, for optimism is that we are making a lot of progress on new technologies. And I think one of the frustrations, of course, in how slow we're going is that it takes time to develop new technology, new science, to feed into the applied science, to feed into commercial opportunities. Solar technologies, first silicon solar cells go back to the 50s, late 50s, and now we're seeing large commercial deployment of solar. Fusion, that you'll hear more about next week, the fundamental science for fusion goes back seven or so decades, and that's just now to the point of possible commercial opportunity. So it takes a lot of time. Good news here is that the pipeline is being fed well by public funding for innovative new science and new technology. Funding for fundamental R&D at DOE is at an all-time high right now. And then, lastly, in the policy area, there are a lot of interesting pieces going on there. I mentioned the credits here, 45Q, which credits for carbon capture and sequestration to incentivize a technology that we will surely need going forward. There are some carbon pricing plans that seem to be gaining traction. I cite the Schultz-Baker plan. Chris Knittel should say more about that since his professorship is named the Schultz Professorship. And then lastly, I think we're all aware that there are a lot of state and regional activities to respond to climate change. California, Texas, the Northeast, and so on. And those, call them experiments, those are large focused efforts. Those are really important and helpful both for learning about what we might do at a national level, but also ways to reflect the fact that the resources that we have in different parts of the country, in different parts of the world, are different, and so how we respond to climate change will be different in different areas. So let me stop there and thank you all. And if there is time, we could take a question or two, say.
Hey, thanks, Bob. That's great talk. I don't know about the time,
Yeah.
Gerald, but there's quite a few questions. The first one is, Bob, about the how did you foresee the use of biomass to liquid fuel, both for industry and for transportation?
Well, so biomass, I've hardly given all of the pathways here. As I said, sesame has some 1,000 plus pathways that are possible. Um, Biomass to biofuels to um, low carbon applications, I think, will be an important part of the system going forward, particularly in a difficult to decarbonize area like air transportation. Right? So that will play a role. I don't see us using biofuels made from food products. I think corn to ethanol or corn to other alcohols that can be used as fuels. I don't see that as a long-term pathway. We're getting better at second and third generation biofuels, so cellulosic biofuels, and that will continue to be, I think, a focus in specific areas.
Okay, thanks, Bob. Just one
Okay.
more question, and then
Okay.
you take from there. The other one is probably from a country other than the U.S. This is asking you that whether or not we should build a robust nuclear energy program, or should we be able to uh, use the grid storage and CCS to meet the low carbon goal?
That's a very good question, and one that we're grappling right now with in the future of storage study. It is interesting to think about where you have particular value added from nuclear. I mean, clearly it's important today in our system. It's 17, 18% of low carbon energy generation. Um, Particularly as we get to deep decarbonization, so 100 grams of CO2 per kilowatt hour, 50, 10, 0, um, then the cost of getting to that deep decarbonization, that 0 grams of CO2 per kilowatt hour, is very high if you try to do it only with variable renewable resources plus storage. Much cheaper if you do that with some zero carbon base, so like nuclear. And so I think continuing to grapple with how do we incentivize that sort of energy resource as part of the mix is really important. And so I think diversity remains a major theme here, and one that we need to keep a focus on.